Welcome, everyone. Today, we are tackling one of the most critical challenges in generative AI, avoiding the hallucination trap. We're going to learn how to identify when Claude is guessing and, more importantly, how to apply advanced strategies to ensure its responses are grounded in absolute facts. Let's get started. Let's kick things off by defining our core problem. What exactly is a hallucination in the context of AI? Simply put, it's when Claude generates text that sounds incredibly confident, but is factually incorrect or completely contradicts the context you provided. Why does this happen? Because Claude, at its core, is a probabilistic engine predicting the next best word. If we don't constrain it, it might prioritize sounding plausible over being factual. For us as engineers and AI practitioners, this is a massive risk. Hallucinations destroy user trust and can ruin enterprise applications. Your first line of defense is simply learning how to spot them, watching for unverified claims or subtle factual drifts that sneak into long responses. Take a look at this flowchart. It illustrates the exact moment a hallucination is born. When a user submits a query, Claude begins processing. The critical juncture is the decision point. Is there sufficient context? If the context is rich and factual, we get a grounded output. But if the context is thin, the model falls back on probabilistic guessing. That guessing path leads straight to the red box, a hallucination. Our goal today is to sever that no pathway entirely. Now let's look at our first and arguably simplest mitigation strategy, giving Claude the permission to say, "I don't know." By default, language models are eager to please. They want to give you an answer, even if they have to stretch the truth to do it. As a prompt engineer, you have to break this habit. You do this by explicitly defining an acceptable failure state in your prompt. By simply writing, if the answer is not in the text, say "I don't know," you create a safe off-ramp for the AI. This deep dive into prompt psychology is crucial. You are essentially relieving the model's pressure to hallucinate. It's a foundational guardrail that dramatically cuts down your false positive rate. This decision tree breaks down the internal logic we are forcing onto the model. When Claude analyzes the query against the context and finds no match, it hits a roadblock. Without permission to fail, it takes the red path and hallucinates. But by injecting that explicit permission into our prompt, we open up the green path. Claude safely outputs "I don't know," protecting the integrity of your application. Moving on to strategy 2, factual grounding using direct quotes. When you are dealing with massive documents, anything over 20,000 tokens, like a dense legal contract, the model can suffer from attention dilution. It might lose track of specific details in the middle of the text. To fix this, we use a two-step prompting technique. We tell Claude, first, extract word-for-word quotes relevant to the prompt inside XML tags. Only after you have those quotes, write your answer. This is a game changer. By forcing the model to write out the raw facts first, you are physically anchoring its attention mechanism to the truth before it synthesizes its final prose. Let's trace this execution in our sequence diagram. You pass a massive 50K token PDF into Claude. Notice the intermediate step. Claude doesn't just jump to the answer. It first outputs the raw, verbatim quotes. This creates a tangible workspace of verified facts. Once that workspace is built, Claude performs its synthesis, resulting in a grounded final response. It's a structured pipeline that guarantees accuracy. Strategy 3 takes grounding a step further: verification and strict citations. In enterprise applications, trust but verify is the golden rule. Your users need to know exactly where Claude got its information. We achieve this by instructing Claude to make its responses auditable. You tell the model, for every claim you make, append a specific citation. If you write a claim and cannot link it to a source quote, you must retract it. This introduces a self-correcting feedback loop. The model has to internally validate its own output before returning it to the user. It severely penalizes fabrication and ensures your users can click right back to the source data. This diagram shows the micro workflow for every single sentence Claude generates under this strategy. It drafts a claim and then hits a validation gate. Can I find the citation? If yes, it appends the citation and moves forward. If no, the claim is mercilessly retracted. This ensures that the final auditable response is a fortress of validated facts, with zero room for hallucinations. Let's dive into some advanced techniques, starting with chain of thought or COT verification. Sometimes, hallucinations aren't just bad facts, they are bad logic. When a model jumps straight to a final answer, it might make a leap of faith. COT fixes this by forcing the model to explain its reasoning step by step before it delivers the final answer. We usually implement this by giving Claude a thinking XML tag to work inside. This grants the model, thinking tokens computational space to process its logic. By externalizing the thought process, Claude can spot its own faulty assumptions and self-correct mid-flight, long before the user sees the final output. Observe the flow of chain of thought in action. The complex query enters the thinking tag. Claude analyzes premise 1, then premise 2. At this stage, it might identify a logical flaw in its own initial assumption. Because it hasn't output the final answer yet, it can execute a self-correction strategy. Finally, it outputs the verified, logically sound conclusion in the answer tag. Next, we have two powerhouse architectural strategies: best of n verification and iterative refinement. Best of n means running the exact same prompt multiple times. If Claude gives you 3 completely different answers, you instantly know the model is hallucinating or guessing. It's a fantastic automated consistency check. Iterative refinement takes a different approach. Use Claude's own output as the input for a second prompt. You literally ask Claude to act as an editor, review this summary against the source text, and fix any errors. You are treating the AI not as a single tool, but as an ensemble system, where a second pass catches the hallucinations the first pass missed. Here we see the architecture of a best-of-n system combined with refinement. The draft generation spins out multiple parallel outputs. An evaluator mechanism, often another LLM prompt, compares them. If one output hallucinates a rogue fact, it stands out against the others. The system strips out those inconsistencies, funneling only the verified, agreed-upon facts into the refined final output. Our final core strategy is external knowledge restriction. Claude is incredibly smart. It has been trained on a massive corpus of human knowledge. But sometimes, that's a problem. If you ask it to summarize your company's private HR policy, you don't want it filling in the blanks with generic HR policies it read on the internet. We have to set strict boundaries. You must explicitly tell Claude, answer strictly and exclusively using the provided documents. Do not use outside knowledge. This deep dive tactic effectively puts blinders on the model. It turns Claude from a worldly philosopher into a laser-focused parsing engine that only knows what you just handed it. This pie chart is simple, but it represents the ultimate goal of external knowledge restriction. 100% of the knowledge utilized for the task must come from the allowed, provided context. Exactly 0% should come from the model's pre-trained general knowledge. By enforcing this strict mathematical split in your prompts, external hallucinations are practically eradicated. Let's bring this all together with a real-world use case. Imagine you are building an AI tool to audit a 500-page mergers and acquisitions report. A hallucinated financial figure here could cost millions. How do we build it? First, we restrict external knowledge so it only looks at the provided M&A report. Second, we force it to extract direct quotes of financial figures before analyzing them. Third, we use chain of thought to evaluate the risk logic step by step. Finally, we demand strict citations for every single risk identified. The result, a bulletproof, hallucination-free audit report. Mastering these techniques is what separates toy AI projects from enterprise-grade systems. Thank you for joining this deep dive. If you found this valuable, I invite you to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Take a look at this final architecture diagram. It stacks all our strategies into a single, cohesive pipeline. We start with the raw M&A report, restrict the knowledge, extract the verbatim quotes, apply our chain of thought logic, and wrap it all in strict citations. The output is that golden box at the bottom, an enterprise-grade, highly trustworthy AI report. This is how you conquer the hallucination trap.